All right, so chapter 12 is about sequences and series. And in this first lesson, we're going to talk about just an introduction to sequences. So we're going to talk about what they are and then how we can find them and write rules for them. So one of the most famous sequences is called the Fibonacci sequence. And we'll be looking at that one. That's kind of a neat one. And a guy named Leonardo Fibonacci was the creator of it, and he actually talked about rabbits in the process of doing that. So, reminder, well, what a sequence is a set of ordered numbers, or an ordered set of numbers. Each number in the sequence is called a term of the sequence. The sequence may be infinite, like the natural numbers, the whole numbers, integers. Those are infinite sequences, or they might be finite sequences like just the numbers 1, 2, 3, and 4. You can think of a sequence as a function with sequential natural numbers as the domain and the terms of the sequence as the range. So when we talk about that, we have like the term numbers. You can only have term number 1, term 2, term 3, term 4. You can't have a term 0. It's not like when we're talking about like a linear equation. So we're going to use subscript notation in writing them. So one of the things that we'll be looking at with our notation is that we'll use a of n is refers to the sequence number, like the nth term. That's one way we'll be talking about it. And let's say the first term could be like a sub 1, second term a sub 2. So we'll be using subscript notation to represent term numbers. So a sub 1, a sub 2, a sub 3 to a sub n, the nth term or the last term of a sequence. So here's an example, and this is actually the Fibonacci sequence here, the start of it. That our term numbers would be our domain 1, 2, 3, 4, and 5, and we use n to represent the term numbers. And then a sub n then would be the numbers 1, 1, 2, 3, and 5, and that would be our range then. So the term number is the domain, the term value is the range. The Fibonacci sequence, or in the Fibonacci sequence, the first two terms are 1, and each term after that is the sum of the two terms before it. So to find, sometimes with finding sequences and how their pattern is, sometimes it's a little bit difficult to get there, but you can do it with using tables usually help you. So this rule can be expressed by saying that a sub 1 is 1, a sub 2 equals 1, and then a sub n would be the two terms before it. So when we say a sub n minus 2, that means two terms before the number we're trying to find. And a sub n minus 1, we refer to the term just before the one I wanted to find. So for instance, if I was trying to find this term here, I would take the term just before it, which would be a sub n minus 1, and then the two terms before it, which would be a sub n minus 2. So that n minus 1 refers to the term just before it, n minus 2 refers to two terms before it. And this is what we call a recursive formula. In a recursive formula, we're going to use the previous answers to get the next answer. So here we have a recursive formula here for this first example. It says find the first 5 terms of the sequence with the first term a sub 1 equal to negative 2 and then a sub n. So to find the next term, this means we're going to do 3 times the term just before it and then add 2 to that. So 3 times a sub n minus 1 means we're going to multiply 3 times the previous term, and then we're going to add 2. so we start with our first term is -2. So to find the next term, I'm going to do 3 times -2 and add 2. Because this means 3 times a sub n minus 1 means 3 times my previous answer plus 2. So 3 times -6, or -2 is -6, plus 2 is -4. So to find the next term then, I do 3 times my previous answer. So 3 times -4 plus 2. So 3 times -4 is -12 plus 2 is -10. So then we do 3 times that answer, -10, and add 2. Which is -30 plus 2 is -28. And 3 times -28 plus 2. So it would be -82. Oops. So the a sub n minus 1, this part here then, means we're multiplying the previous answer times 3 and then adding 2 to it. So this just represents a sub n minus 1 means the previous answer. If I said a sub n minus 2, then it would be the answer before that one then. It would be 2 before that one. All right, so let's look at another one. No, you go ahead and do it. So here's our answers to the, check it out. Now one thing that, a different way of thinking about the recursive formula is using the words now and next. So you could think of it as, in this case here for B, I could say, to get my next answer, I'm going to take the answer I have now and multiply it by -3. So to get the next answer, in this case, so we started with 2, that's the answer I have now. To get my next answer, I would multiply that by -3. And then get to my next answer, I would multiply that one by that answer by -3, and so on. So you can also think of it as like a next now statement is another way of thinking about it. All right, explicit formulas. Explicit formulas are like what you would see with your y equals. That instead of using previous answers, we're going to use the term number to get our next answer. So it would be like, it would be like a y equals situation. So here where it says find the first 5 terms of this sequence, we could think of that as the same as y equals 3 to the power of x minus 1. Where all I'm going to do is put in the term number for n to find my next answer. Find that answer then. So recursive formula, I take the answer I have now to get my next answer. Explicit formula, we just put the term number in for n, and that gives us our new value. So for instance, so a sub 1 would be 3 to the first power minus 1. Okay. Or 2. So then a sub 2, the second term then, would be 3 raised to the second power minus 1. And so on. So recursive, we use the previous answer to get the next one. Explicit, we just use the formula and the term number. Okay, so once again, when we're talking about a recursive, that means we're like now next. Okay, we're using the previous answer we had to get the next answer we want. And then if it's explicit, then that means we're just going to plug the values in for n. Plug the term number in for n. All right, now we're going to look at trying to, given a sequence, finding the rules for that sequence. A reminder of, first of all, sometimes we need to figure out what kind of sequence it is. Is it exponential? Is it linear? Is it quadratic? So we have to use our rules for finding first, second differences and constant ratios to figure out which kind of rule it is first. And then the easiest way to write an explicit rule is to actually make a table and use that table to figure out the specific rule that we're talking about. So first of all, we need to figure out what kind of a function is this. Is this exponential? Is it linear? Is it quadratic? So here we've got the terms 5, 10, 20, 40, and 80. So is this linear, quadratic, or exponential? We can do the first differences. First of all, so 80 minus 40 is 40. 40 minus 20 is 20. 20 minus 10 is 10. And 10 minus 5 is 5. So those are not the same, so it's not linear. So we find the second differences. So we get 20. 40 minus 20 is 20. 20 minus 10 is 10. And 10 minus 5 is 5 again. So it's not linear or quadratic because the first and second differences are not the same. So then we should try ratios. So we divide 80 by 40, and we get 2. 40 by 20, we get 2. 20 by 10, we get 2. And 10 divided by 5 is 2 also. So that means that this is an exponential function. So what do exponential functions look like? Do you remember? Okay, the variables at the top. So an exponential function, if we're talking about a y equals, then we would have said y equals a times b raised to the power of x. A was always our starting value, and b is our ratio, okay, our constant ratio, which in this case would be 2. So what we're going to do is we're going to look at how this works with the table. So first of all, we're going to put in the first column of our table, we're going to put the term number. 1, 2, 3, 4, and 5. And then we're going to put an n right below that one. In the second one, we're going to put the term. Okay, what do we get there? We have 5, 10, 20, 40, and 80. And then we're going to talk about how did I get there? Okay. In terms of our constant ratio or our differences. So to get 5, or let's see, to get 10, we did 5 times 2, right? Okay. Our first term we had is 5. There's our value of a at this point in time. All right. So then how do I get from 5 to 20 then? To get from 5 to 10, we multiply by 2. How about to get from 5 to 20? Okay, we multiply by 4, right? But multiplying by 4 is the same as multiplying by 2 twice, right? So this would be 5 times 2 to the second power, right? Because all I did is multiply by 2 one more time, didn't I? Okay. To get from 20 to 40, we multiply by 2 again, right? So that means this would be 5 times 2 to the third power. And then 5 times 2 to the fourth power to get 80. So basically, we just keep multiplying by 2, don't we? Okay. So what about the nth term then? Well, the nth term is going to be 5 times 2 raised to some power. Well, what we want to do then is we want to compare these numbers here, the exponents in this case, with the term number. How do those exponents compare to the term number? They're what? They're 1 less. So then this is going to be 5 times 2 raised to the power of n minus 1. So our explicit rule would be a sub n equals 5 times 2 raised to the power of n minus 1. Because these exponents here are each time 1 less than our term number. Okay, let's look at another one. Right, so we'll look at the first difference. Almost read that. 11.5 minus 9 is 2.5, right? 9 minus 6.5 is 2.5. 6.5 minus 4, and then 4 minus 1.5. Okay. So the first difference is a constant. So that means this one's going to be linear. So what do linear equations look like? Okay, y equals mx plus b. Okay. Except we're going to be using n and a sub n. So we'll have, when we're done, we're going to have a sub n equals, well, we can use mn plus b. Okay, where n is our term number. So we'll make a table here again to do this. So we have our term number first. 1, 2, 3, 4, 5. And then our terms. And we're always going to start with that very first term. And what does it take to get from that term to the next one? So to get from 1.5 to 4, what did we do? We added 2.5, right? Okay. So this was 1.5 plus 2.5. Got us to 4. Okay. And then to get to from 4 to 6, what did we do? We add another 2.5. So this would be 1.5 plus 2.5 times 2. To get to 9, what did we do? add it again, right? So it would be 1.5 plus 2.5 times 3. And then so on for, right? So we need to find the nth term then. So find the nth term. We have 1.5 is here in each of these, okay? Plus, we added 2.5 times some number. Well, how does this value here, how does this number here compare with the term number? How does this 4 here compares with term number was 5, right? So it's 1 less. So this would be 1.5 plus 2.5 times the quantity n minus 1. So a sub n equals 1.5 plus 2.5 times n minus 1. And then that's a function that we can simplify, so we want to simplify that too then. So we'll distribute the 2.5 and simplify it. And then you could write it either way. So in this situation, our slope would be 2.5, so we'd have 2.5n minus 1. So whether you wrote it either of these two is fine. Right. But, so what do? We made a table. First column, term number. Second column was the term value. And then we use that from our starting number, the very first number we had. Okay, what did I use from that number to get the next one? And then to get the next one after that, to be able to get that explicit formula. All right, so here we have a physics application. It says a ball is dropped and bounces to a height of 4 feet. The ball rebounds to 70% of its previous height after each bounce. Graph the sequence and describe its pattern. How high does the ball bounce on its 10th bounce? So, ball is dropped and bounces to a height of 4 feet. So on the first bounce, it is equal to 4, right? On the second bounce, all right, so our first bounce, it's at 4 feet. On the second bounce then, it says it only goes to 70% of that. How do I get 70% of 4? Okay, so we have 4 times 0.7, which is 2.8, right? Seven times 4 is 28, right? Okay. So the original bounce comes back up to 4 feet. On the second bounce, then it only goes to 70% of that. So then on the third bounce, it's going to go to 70% of that, right? Which would be 4 times 0.7 squared, correct? Because I'm going to multiply by 0.7 again to get to the next number. So what's 2.8 times 0.7? 1.96. All right, so okay. Then to get to the fourth bounce, we multiply by 0.7 again, right? So it's going to be 4 times 0.7 to the third power. Which is what? Okay. So it's going to be about here. All right. So this graph is, so it says describe the graph the sequence. Right? So we can keep going with that. And to do that, now one of the things, here's another thing you can do, is that you can just take your calculator, and in most sequences you can do this. We just start out and we put the very first number in there. Okay, the number is 4. Okay, and then we're going to multiply that by 0.7, right? And the nice thing about your calculator is that it has this last answer feature. So all I need to do is I can just keep pressing enter to get to my next numbers. And it will take the previous answer, multiply it by 0.7. This is actually a recursive formula here. Okay? Because I'm doing my now answer, multiplying it by 7 to get 0.7 to get my next answer. Hit it again. There's our 1.372. One more time, then we get 0.96, and then so on. So let's see, 0.96 is the fifth one, right? So then we go 6, 7, 8, 9, and 10. So on the 10th bounce, it would be 0.16 feet high. So we have two ways of doing it. You could take your calculator, type in 4, and then multiply it by 0.7 until you get to the term number you want. Or we have a rule here then. The nth term would be 4 times 0.7 raised to the power of n minus 1. So we would have, because the exponent here is always 1 less than our term number, so we would have an explicit formula here. A sub n equals 4 times 0.7 n minus 1. Or we could do a recursive formula also, which would be 0.7 times a sub n minus 1 plus 4. Or starting at 4, excuse me, that would be starting at 4, where a sub 1 equals 4. Almost messed it up. Where a sub 1 equals 4. So we have a explicit rule or a recursive rule. We could use both of those. So to find my 10th term, on my calculator, I can either do 4 times 0.7 raised to the 9th power, because we're doing 10 minus 1, and get 0.16. Or we could type in 4 and then multiply it by 0.7. So 4 was our first term, 2.8 was our second, so then third, fourth, fifth, sixth, seventh, eighth, ninth, and our 10th term. So either way you use it, we can find out that the 10th bounce, it is 0.16. Sure, get the right units here. Okay. All right, so with these, you can use explicit rule or you can use recursive rule to get to your answer. So what's this doing here? That says describe its pattern. The pattern is it's decreasing at a decreasing rate. The amount of gap between each dot then is getting less and less each time. So I could say it's decreasing at a decreasing rate. Okay. All right, one more. Iterations. Recall that a fractal is an image made by repeating a pattern, which is just a sequence. Each step in this process, in this repeated process, is called an iteration, the repetitive application of the same rule. So here we have this example 5 here from the book. This is right out of the book, and I wanted to use it to talk about this. It says the Sierpinski triangle is a fractal made by taking an equilateral triangle, removing an equilateral triangle from the center, and repeating for each new triangle. Find the number of triangles in each next iteration. So first of all, we went in the first triangle, we have one triangle there. We take a triangle out of the center, here, and we can see that we now have 3 triangles. So we went from 1 to 3. When I take triangle out of the center of each of those triangles, I now have 9 triangles. So then if I took a triangle out of each of those, I would have how many? Well, what did we do to get from 1 to 3 to 9? We're doing what? Multiply by 3. Okay? So every time I do take a triangle out of the middle, I'm creating 3 more triangles. So the next one then would be 27, and then the following one would be 81, because we're just repeating that pattern of continuing to take 3 out. So we're multiplying by 3 each time. So in this example, they want us to find the number of triangles in the 7th and 8th iteration of the Sierpinski triangle. So the 4th and 5th are there, 27 and 81. So to get to 7th and 8th, all I have to do is what? Okay, I can do 3 raised to the 7th power minus 1 for the 7th iteration, because they're using this formula, and 3 raised to the 8th power, or to 8 minus 1 to get the 8th one. Or we could just take 81, multiply by 3, and that would give us the 6th iteration. Then multiply by 3 again to get the 7th, and multiply by 3 again to get the 8th. So we have our options then with our calculator. We could do 3 raised to the power of 7 minus 1, or 3 raised to the power of 8 minus 1 to get our 7th and 8th iteration. Or we could just take 81, which was our 5th term, multiply that by 3, and we get our 6th term. Multiply that by 3 to get the 7th, and multiply that by 3 to get the 8th. So you have both options available to you to determine which way you found that last answer. So either way works. Okay. Any questions?